Now the oxygen has 8, 4 of its own and 4 that are shared. The nitrogen has 8, 2 of its own and 6 that are shared. And everybody's got their preferred number of bonds. Question with that? How do you know to do that and not this? That would still give nitrogen an octet.
Chlorine only wants one bond.
Chlorine only wants one bond, right. Chlorine is not going to do that. Fluorine, chlorine, bromine, iodine, everybody in that column just wants one bond, and so that's, chlorine is fine the way it is. It's going to happen over here, it's going to happen from that oxygen. And that would be your finished structure. Question with that?
Does it matter if you have oxygen on the left versus oxygen on the right?
No. What matters is that you've got the oxygen double bonded and the chlorine not, and all your dots where they're supposed to be. Question about this. Do HCN.
Why are the dots not separated of the end?
Because every electron you've got in these structures has to be paired. Orbitals hold a pair of electrons, and so every electron is paired. Whether it's bonding or not bonding, they still have to be paired. That's why I'm always placing the dots in pairs. While I'm thinking of it, commercial break here. I'm still need, as far as the triathlons go, I still need 2 people for Sunday, 1 for morning shift and 1 for afternoon shift. So if you're able to do that, that's bonus points. Other thing, not bonus points, but as far as science club trips go, October 13th, that's the Tuesday of fall break. We're going up to do the Virginia Creeper Trail bike ride. Bike rentals, the club is paying for the bike rentals. Your only cost would be $10, which goes toward the school van to get folks there. So you pay $10 to the club, and you buy your own meals on the trip. And otherwise, it's a free trip. So if you want to go on that, I need to know fairly soon so that we can get the bike reservations made. And the other tours that are up there, the nuclear power plant, the glassware factory, we can talk more about those later. Those deadlines are not as urgent, but the Creeper Trail thing is actually only like less than 2 weeks away. So we need to kind of get that finalized. So if you're interested in doing any of those, but especially the Creeper Trail one, get in touch with me soon so we can get your spot in on that and get the reservation made. It's set for the 13th, Tuesday. But if the weather's looking really bad that day, we may shift it to the 12th, which is the Monday. Anyhow. Rule number 1, who's the central atom? Carbon. Rule number 2, how many total valence electrons do we have to divvy out? 10. Rule number 3 is connecting into the center, correct? So that's placing 4 of the 10. There's 6 more to go in as dots. And we start with those on the perimeter, but they don't go to hydrogen because the hydrogen's already full, correct? 2, 4, 6, and that fills up nitrogen. Is that your finished structure? Now remember, with Rule 5, I said that's pretty much an oxygen rule. It's not exclusively oxygen. You find it in this, and you'll find it in a few other structures. It's just that most of the time it's oxygen. The problems with that are carbon does not have an octet, carbon does not have its preferred number of bonds, and nitrogen does not have its preferred number of bonds. Do you see that there's 3 structural problems there? The hydrogen's happy, but nobody else is. And you need to fix that by folding in if you can. So this nitrogen will fold in a pair of electrons. Is that much better? Not really. And if it does it again, then that's better. Because now everybody has an octet, everybody's got their preferred number of bonds, that's your stable structure. That would be your finished structure. Is there a question about getting there? All right. Steps 1 and 2 are on the board. Step 3 would account for 4 of our electrons. Step 4 would place the remainder like that. And that's what you should have at the end of step 4 before you start looking at it more visually. Less mathematically and more visually. Is that the finished structure? No. How do you adjust it? And so we would do that of converting a pair into a bond from the oxygen, not the chlorine, and that would be your finished structure. Does your oxygen have an octet? Go ahead.
Can you explain why it wasn't a finished structure in the first place?
Because it doesn't line up with what you've got over here about these atoms.
Can you explain it a little bit?
Sure. But when you look at those numbers on that chart and compare that to the structure, does oxygen have 8 electrons? Yeah, it does. It has 6 of its own and access to 2 through sharing. So it has, the oxygen has 8 now, right? The way it's drawn at the moment, it's got 8. Does it have its preferred number of bonds? No. has 8, has 1 bond. Boron doesn't have 6 electrons, and it doesn't have 3 bonds either. So you got multiple problems in here, right? But that can be fixed by oxygen taking a pair of electrons and converting that into an additional bond. And like I said before, it's not a matter, you're not trying to figure out if oxygen will make that extra bond. You're trying to figure out how it's going to do it, right? Because it will get a second bond. It's impossible to prevent it from getting a second bond. It's just a matter of what's going to happen when it does get the second bond. And so the oxygen throws in, it gets the second bond. Now the oxygen has 2 bonds, so that's been corrected. The boron now has 3 bonds, and it now has 6 electrons. And every atom's got what it's supposed to have in order to be stable. The octet thing and the preferred number of bonds thing are things you look for to determine if it's stable or not. And it's going to shift electrons around to become as stable as it can. And that would be a stable structure.
Because each of those dashes mean 2
Right.
bonds, and now it has its 6, and it has its 3 bonds.
Correct. Correct. Is that any better?
Yes, definitely.
Okay. Next one. And this is our first one that has a charge on it. We've got a nitrogen, we've got 2 oxygens. Oxygen is the more electronegative atom, so oxygen's on the perimeter, nitrogen in the center. When you do the tabulation here, the nitrogen contributes 5, each oxygen contributes 6, but that positive charge means you've actually lost 1 electron, correct? So this is 5, 11, 17, 16 actually, 16 valence electrons to be accounted for, because one of those 17 has wandered off somewhere. There's 16 valence electrons to be apportioned. 16 valence electrons. And there's 4 of them. Connecting perimeter into the center, that's 4 of them. That means there's 12 more to go. Starting those on the perimeter, that's 2, 4, 6, 8, 10, 12. All of those are placed on oxygen. And that's what you get at the end of Rule 4. This oxygen only has 1 bond. It's going to fold in a pair to make an additional bond. What does that do to nitrogen? Gives it 3 bonds. Does it have an octet?
Yes.
No. The other oxygen will do the same thing. What does that do to nitrogen?
Gives it an octet.
It gives it an octet, but it also gives it 4 bonds when it would rather have 3, right? So, what's a good way to say this? Oxygen wants 2 bonds, it's going to get its 2 bonds. Nitrogen wants 3 bonds, tough. That's life. It's stuck with 4 bonds, right? And it's oxygen's fault because oxygen's the one that's in control, because oxygen is the higher electronegativity atom. In terms of reactivity, electronegativity is everything. Oxygen is the more powerful atom, it's going to get what it wants. And nitrogen's going to get what oxygen lets it get, which in this case, it lets the nitrogen get an octet, but it has to do 4 bonds to do it. Now, as a matter of notation, anytime you're dealing with an ion, whether it's cation or anion, you put the structure in brackets and you show the charge outside the brackets. You use brackets if it's charged. You have to show the charge because that's part of the structure. But if you don't use brackets, then it looks like an oxygen bonded to a nitrogen bonded to a positively charged oxygen. And that's not what you've got. This is a polyatomic ion, and the charge is distributed over the whole thing. And hence the brackets. And that is rather similar in structure to carbon dioxide, correct? That's a very carbon dioxide-ish thing. Do you see how this is a similar structure to this? And the driving force that makes it that way is oxygen obtaining a second bond. That's the dominant factor to consider. Question about that? All right. Is this going to be as stable as CO2? How do you know?
Because the nitrogen's not happy.
Because the nitrogen's not happy. That's right. In this one, everybody's got their octet and everybody's got their preferred bonds. That means stable. This is not quite as good, right? Everybody's got their octets, but not everybody has their preferred bonds. Therefore, less stable. All right. I'll leave that one up for a minute. NO2 negative. Take a minute and work on NO2 negative. Got your close. Formula says 18 electrons. This is going to be 4 of them, just simply connecting into the center. 14 more to go. That's 2, 4, 6, and the oxygen's full. 8, 10, 12, and that oxygen's full. There's 2 more to go, and they have to go on nitrogen. That's the end of rule 4. Then we look at our oxygens. This one will take a pair of electrons, fold it in. That gives it 8 electrons, 2 bonds. The nitrogen has 8 electrons and 3 bonds. That looks good, right? Until we get over there. Because now, this oxygen doesn't have a second bond. And if it takes a pair of electrons and folds them in, which it will do, that would put nitrogen beyond 8, wouldn't it?
Yeah.
And that's not possible. or at least not formally possible of what we talked about there. 8 is the absolute limit for nitrogen. And so what happens is this, if you think about this chronologically, this oxygen will force that pair of electrons in, which means for a fraction of a second, you've overloaded this nitrogen and something's got to go. And so what happens is, this one gets bumped back out. And now the oxygen on the right is happy. But the one on the left is mad at you, right? And so then this one forces that back in, and that one bounces out. And you get this perpetual flip-flop, flip-flop, where they're competing over who gets the second bond. And if you think about that happening zillions of times per second, then it's really mathematically like a bond and a half each. If sometimes it's got the double and sometimes it don't, then, I mean, it's not perfect, but it's better than nothing. And it's certainly better than the oxygen being stuck with one bond all the time, right? This kind of situation is called resonance. And the resonance is an attempt to do what this one already did. That resonance over there is an attempt to get each oxygen a double bond like they have here, like they have in CO2. That oscillation is a result of oxygen getting a second bond. Now there's two ways to indicate that. You could either draw both structures, meaning draw it like that, and the other way. But when you get into things that have 3 or even 4 resonance structures, that becomes a lot of drawing. So rather than draw all the extremes, you can just draw one and write the word resonance, and that lets me know that you see what's going on. Question about that. Do you see that the driving force in that one that causes resonance is exactly the same driving force you had here? And that's getting oxygen a second bond. It played out a little different because this nitrogen had a lone pair that this nitrogen didn't. And so folding in for a double bond put oxygen at 8, whereas here, folding in for an extra bond put nitrogen beyond 8. And that's what set up the resonance. Resonance is an attempt to get equal bonding to those oxygens. I mean, oxygen is the same as oxygen, right? There's no good reason that you would double bond one and single bond the other. The energies are identical. And so you end up with this resonance situation. It's an attempt at equal bonding to be more like this, or more like CO2. So this is another one that's marked in the notes for reference. CO2 is very stable in its own right. This is a variation where the central atom is forced to go beyond what it preferred. This is a variation where you set up a resonance. But it's an attempt to do the same things as CO2. Question about that? Then draw the structure for carbon on your own. Resonance is an attempt to bond to equal atoms in an equal fashion. What's on the board now is the end of Rule 4. And then you look suspiciously at your oxygens. Will this one fold in a pair? Yes. And that puts carbon at 8, right? Will this oxygen fold in a pair? Yes, but what happens as a result?
Yeah, the one will break off.
Which means you've got
Resonance.
resonance going on. And then this one's going to do the same thing, right? I mean, all three of these oxygens are in on that trying to do the same thing. And so, resonance, and since we're dealing with an ion, brackets in charge. If you're going to draw out resonance structures, you'd have 3 variations on this, where the double bond is here, there, and top, right? Either draw all 3 structures, or just draw one of them and write the word resonance. The key thing is that you recognize there is resonance. So there's not a good way to draw resonance, really. But you need to recognize it when you see it. And this is an example of it. Question?
I have a question.
Yes, go ahead.
Why does it keep shifting around? I think I wasn't here when you explained.
Well, it's because the oxygens, when you compare to that chart over there, oxygens prefer to have 2 bonds, right? That's what makes them most stable, okay? And in terms of electronegativity, the only atom more powerful than oxygen is fluorine. Fluorine has the highest electronegativity. Oxygen is a very close second. And so when they're fighting over electrons, nobody beats fluorine. And nobody but fluorine is going to trump oxygen. And so oxygen will get its octet, and it will get its 2 bonds one way or another. And that's why different things over here happen to poor nitrogen based on how oxygen was getting its 2 bonds. And that's what's happening here. You've got 3 oxygens all needing a second bond. And carbon just can't handle more than 8 electrons. And so for each of them to fold in a pair simultaneously and have a true double bond each, that's just not possible. because carbon can't handle 2, 4, 6, 8, 10, 12 valence electrons. So that's not an option. And so what you have instead is this oscillation, where one folds in and that bumps another out, and just perpetually, fold in, fold out. The driving force is oxygen getting a second bond, but the limiting factor that makes it turn into resonance is carbon's absolute limit of 8. Now there are some atoms, don't write this down just yet. I'm just going to generically say X here. There are some atoms that can handle more than 8, and so in some cases you will get a true double bond each like that, all right? But carbon's not one of them. Carbon's limit is 8, and so that's just not going to happen for him. The atoms, who is X, who are the atoms that can go beyond 8? That's rule 6. You'll be happy to know there's only 6 rules, all right? And we've already covered 5 of them. So, and we're not going to be able to do rule 6 in the next 11 minutes, all right? So between now and next class, get really, really, really good at rules 1 through 5. Then we'll throw rule 6 on there, and then we'll move on to shapes and patterns and bonds and signals and pies and things of that sort. Right? Get good at rules 1 through 5 by Monday.